Hello, my name is Jason Koenig, and I'm here to talk about adaptive restarts for stochastic synthesis. I want to start by describing stochastic synthesis, and that'll let us talk about its behaviors. Then I'm going to explain how restart strategies lead to our adaptive restart algorithm, and then present our experimental evaluation, as well as future work and conclusions. Stochastic synthesis is an example of a technique for program synthesis, which is the problem of generating a program satisfying a specification. For us, a program is going to be an acyclic data flow graph where the operations are analogous to the x86 instructions. And a specification is going to be a fixed finite set of input-output examples called the test cases. Stochastic synthesis at a high level starts with a program and makes random changes called moves to that program to obtain new ones and is guided by a cost function. And then this process is repeated until the correct solution is discovered. So I want to start with the moves. And given some current program, the move is going to generate a new program. So one example is we could redirect an edge from one node to another, or we could replace an operation with a different one, or we could generate a new node entirely. Because we select which nodes and which operations, et cetera, entirely at random, we're going to need some way to guide this process. And we're going to do that with a cost function. So a cost function is a way to compare the output of the program with the reference from the test cases. So if we have some output and a reference, one possible cost function is to count up all of the bits of difference between them and use that as the cost. But we're going to investigate several other cost functions in our evaluation. So with the moves and the cost, we can now define the stochastic synthesis algorithm. Here we're going to have a loop where at each step we're going to propose a new program and then look at the cost of that program compared to the cost of the old one. If the cost is smaller, we're going to accept the new program as the current one. And we also are going to accept if the new cost is at most this amount X larger than the current cost. And this X factor is going to be drawn from an exponential distribution on each iteration. And the idea here is to prevent us from getting stuck in local minima of the cost function. So now we can look at the behavior of stochastic synthesis. So here is a run of synthesis where we've plotted the cost over time. And here we're measuring cost in iterations and plotting it on a log scale. We can see that the cost has long flat regions that are punctuated by sharp drops in the cost. And we call these flat regions plateaus. We can get a little bit of a better idea of what's going on by plotting a whole bunch of searches all on top of each other. And what we see here is not only do these searches all have these long plateaus, but in fact, they're have the plateaus at the same costs or very similar costs. And these suggest that there is some kind of underlying structure here in the syntax or semantics of the programs that are being explored. So we would like to zoom in and look at the intermediate states that the search is progressing through in order to get a better idea of what's going on. The problem is that these intermediate states are really complicated. And because we're making all these random changes, they often have a lot of extra dead code or code that doesn't affect the program very much, but nevertheless makes them very different syntactically. And this is a problem for both manual inspection as well as trying to understand things in an automated way. So what we're going to do is we're going to simplify the problem. And we're going to do that by doing stochastic synthesis in the normal way, but drastically limiting the number of operations that we're going to support. We're also going to add a new kind of move that has the effect of reducing redundancy in the program to help ensure that we have fewer total number of programs that we explore. And then we're going to look at the synthesis for this specific example program, which takes the input and ORs it with a shifted copy of itself. So in order to actually show what the search is doing, we're going to represent the search as a Markov chain. And this is possible because the algorithm is memoryless. The only state that we propagate from one iteration to the next is the current program. And that means we can create a Markov chain with the programs as states. And we can then also compute the probability of transitioning between two states as a combination of the underlying move proposal probability along with the probability of accepting that based on the relative costs. And this allows us to draw a Markov chain where the states are labeled with, in this case, little expressions representing the program, and the weight of the arrow represents the relative probability of taking each transition. And notice here, we're going to omit any self loops, which are actually going to be, almost every node is going to have a self loop. So this is the Markov chain representation of our target program. And there's a lot going on here, so I want to just point out the highlights. The synthesis starts on the left with the 0 state, and then it bounces around the Markov chain until it gets to the goal state in the bottom right. And there's kind of two main areas of interest in this diagram. And the first, this large central region, corresponds to programs that are basically the identity program. And what we want to observe here is that there's a lot of connectivity between the states of this region compared to the amount of connectivity outside of this region. And for this reason, we're going to call these areas of the search space strongly connected components, because the search is going to spend, once it reaches this component, it's going to spend a lot of its time traversing between states within the region as opposed to leaving the region. There's also something interesting going on in this upper right component. And what's happening here is that the cost of these states is significantly lower than the main component. But because they have both a shift left and a shift right, they end up dropping one of the input bits. And because these shifts are nested, we can't drop either one without resulting in a very large increase in the cost. So this upper right component represents a local minima in the search space. And as we can see, it is possible for there to be a transition to the goal state, but it's just very rare because it requires either a large increase in cost or several moves to occur in a specific sequence. So we can see some of this kind of local minima behavior in full examples. And what we have here is an example of a synthesis problem where some of the synthesis runs hit a common low cost plateau and synthesize relatively quickly. And then there's another set of these runs that retain a very high cost for a long period of time before finally synthesizing. And these searches on the right here take many more iterations, millions and millions of iterations compared to the ones that hit the low cost plateau. So we can assume that they are hitting some local minima of the search space. Now, this behavior where some of the runs take much longer is actually a very common feature of synthesis times. So if we look at the distributions for many different examples and plot them in log space, we see that they often have heavy right tails, which means the longest runs are orders of magnitude more expensive than the shortest ones. And there's a natural way to solve this problem, and that's by using restarts. The idea here is that we want to pick a particular cutoff, and then if we reach that cutoff by running too many iterations, we're going to restart the search in hope of finding a shorter run. And then a restart strategy is going to be a way to pick these cutoffs. And in general, it's going to depend on how many times we've restarted before. Now, there's been many restart strategies that have been proposed in the literature, but we're only going to look at one of them here, which is the Luby restart strategy. So in Luby restarts, we're going to choose cutoffs that are a constant times an element from this Luby sequence, and this is a recursively defined sequence. The advantage of doing Luby restarts is that it's been proven to be theoretically optimal under a black box assumption. And the black box assumption means that the restart algorithm isn't able to observe any properties of the search other than whether it's completed or not. So we're going to use the Luby restarts as inspiration for our adaptive restart algorithm. In particular, we're going to keep the same allocation of search times to the different power of 2 cutoffs. But we're going to relax this black box assumption. And we're also going to run the searches in an interleaved manner rather than running them one after another. So the classic Luby algorithm, when it restarts, it forgets about an old search and it never comes back to it. In our algorithm, we're going to retain those old searches and come back and spend some more search time on them. I want to emphasize here that we're not doing parallelism. So we're not running the searches at the same time. We're just running them in an interleaved manner. So the key point here is that we are going to prioritize the searches with a low cost. And the idea is that the low cost searches are more likely to be close to a solution than the high cost searches. So I'm going to explain the adaptive restart algorithm by example. And the adaptive restart algorithm maintains a binary tree of searches. Each of the nodes is going to be labeled by both the time that's been spent at that node, as well as the cost of the search, the current cost of the search at that node. So we're going to start by running one time unit of search. And here a time unit is going to be something like, say, 10,000 iterations. And we're going to get some cost after we do that. And to continue, we're going to add 2 leaves to this node, and we're going to run 2 more searches, also of one time unit, and we're going to get 2 more costs. So now the key point here is that we're going to compare the cost of the child with the parent. And if the child is smaller, we're going to swap them. And this is going to have the effect of always making sure the lowest cost searches get moved up the tree towards the root. So in this case, we're going to swap these 2, and then we are going to double the amount of time we spend on the parent. And this is going to have the effect of running more iterations on whatever search ends up in that position. So in this case, maybe we get a small decrease in the cost by running for more iterations. Now, to continue the algorithm, we're just going to repeat this process in a depth-first manner. So we're going to descend into the left subtree and then add 2 new searches, both for one time unit. We're going to see in this case that both of the costs are larger than the parent, so there's no swapping. And then we're going to double the amount of time we spend in the parent node. In this case, maybe the cost doesn't change because we're on a plateau. Now we're going to do the same thing in the right subtree. We're going to add 2 new searches. We're going to see that one of these searches is smaller than its parent, so we're going to swap it. And now we're going to double the amount of time we spend in the parent node. And in this case, we get a decrease in the cost. And that means that we need to swap this search with its parent. And then after we do that swapping, we're going to double the amount of time we spend in the parent. In this case, now running 2 units of time. And then maybe we get an even better increase in or decrease in the cost. So the adaptive restart algorithm is going to repeat this process in a depth-first way until we come across a cost 0 or a correct program. So the adaptive restart algorithm has the advantage of spending most of the time on the lowest cost searches. And this is going to work well when the cost is a good predictor of the time to finish for a particular search. We can construct a Markov chain where this is the case. Here we have a Markov chain where there's 2 states with different costs, and the 20 cost state has a significantly higher chance on each step of reaching the goal state than the higher cost state. And because the adaptive restart algorithm spends most of its time on that low cost state, it will do better than the Luby algorithm on this Markov chain. If we swap the cost without changing the probabilities, though, the reverse will be true. In this case, the Luby algorithm has the same performance, but the adaptive algorithm is going to spend more of its time on the low-cost state, which is now further away from the solution. Unlike the Luby algorithm, we don't have a theoretical characterization of exactly when the adaptive algorithm is going to do better or worse than the Luby, and we consider that an interesting area for future work. So even without theoretical results, we can still run an experimental evaluation. And we compared our adaptive restart algorithm against the naive algorithm, which doesn't do any restarts, and the Luby restart algorithm. We did our comparison on two different benchmarks, one from the Steigus competition and one that we obtained by scraping the basic blocks from executables. We performed our experiments with three different cost functions, and we did two experiments, one to compare the beta parameter and another to compare the overall performance of the different algorithms. So this first experiment is to investigate the effect of beta on the search. And recall that beta is this parameter that controls the scale of the allowed increases in the cost at each step of stochastic synthesis. And so we can plot the failure rate of the various algorithms as we vary beta, where in this chart, lower is better. Here we can see as we decrease beta, the naive algorithm starts to get worse and worse from its optimum point. And this is because as beta tends towards 0, the local minima of the search becomes stronger and stronger. It becomes more difficult for the search to escape them because increases in the cost become more and more penalized. The naive algorithm doesn't have any way to escape these local minima, and so the performance suffers. Whereas both the adaptive and Luby algorithms can use restarts to escape these local minima. In the other direction, as we let beta tend towards infinity, the search becomes closer and closer to a random walk. So if the allowed increase in cost is extremely high, then the cost function isn't going to provide any guidance for the search. And so the probability distribution of the probability of transitions is going to become solely dependent on what the moves propose. So we can use the lowest point on each of these curves as the so-called optimal beta for each of these algorithms. And this is going to allow us to compare the performance of the algorithms with the best possible beta for each of them individually. So our performance experiment was to take all of the synthesis problems that we have across our benchmark. There's a total of 1,600 of them. And for each combination of algorithm and cost function, we're going to run each synthesis problem for 50 trials, where each trial can use up to 100 million iterations. And this 100 million iteration limit is important for practical reasons, but it causes a little bit of a problem, which is that we can run into a situation where a synthesis problem succeeds for one algorithm but doesn't for the other. And then we can't really compare a speed up. We can't compute a speed up ratio between them. To solve this, we're going to use a kind of standard technique, which is to use a cactus chart. And in a cactus chart, we're going to take each algorithm and essentially sort the series of expected iterations for each synthesis problem. And this will let us see how each algorithm scales as the problems gets more difficult. But it means that when we're comparing a particular point in the chart, we're comparing, say, the 50th fastest synthesis problem for each algorithm, and not necessarily exactly the same synthesis problems. So this is the resulting cactus chart for one of the cost functions that we compared with. And here the vertical axis is the expected iterations, where lower is better. And we can see that the adaptive algorithm always, essentially at every rank, outperforms both the Luby and the naive algorithm. We can also see that the adaptive algorithm outperforms the Luby algorithm about as much as the Luby algorithm outperforms the naive algorithm. By comparing a horizontal line on this chart, we can also see that the adaptive algorithm within any given cutoff is able to synthesize a higher fraction of the benchmark than the other techniques. We can present these results numerically by comparing a ratio at a particular rank. And we're going to do that in this table. So what this table shows is that depending on what rank and cost function, et cetera, you look at, the adaptive restart algorithm is up to about 10 times faster than the naive algorithm, and up to about 5 times faster than the Luby algorithm. So I want to take a moment to discuss some of the future directions that we could take this research. The first one is to understand the relationship between cost plateaus and strongly connected components in real examples. So we saw that the noise in the syntax of the programs makes this difficult, but it'd be interesting to investigate ways to see past that noise. The next point is to develop algorithms that can recognize the plateau structure of a search in progress and then adapt the search to take advantage of that. For example, by adjusting the moves that are proposed or adjusting beta at the longer a search has been on a plateau. Finally, it would be interesting to theoretically characterize the performance of the adaptive restart algorithm and understand when it does better or worse than the existing Luby algorithm. In conclusion, we showed that plateaus are a key behavior for understanding stochastic synthesis. We also showed that tuning the beta parameter is important to prevent the search from becoming a random walk, and that tuning is easier with adaptive restarts because it works well with a much wider range of betas. Finally, we showed that adaptive restarts are effective for improving stochastic synthesis, both in terms of the runtime and the overall success rate.